everybody. Welcome to the 20th Ockham lecture, which today is dedicated to fusion energy, and so I hand over the task of introducing the speaker to Steve Cowley, who is running the fusion energy program in this country.
Thank you, Alex. You're always a bit nervous when Alex introduces you, because well, if you know Alex, you know why. Per Helander, today's speaker, is one of the foremost plasma and fusion theorists in the world. And he started his career at Chalmers in Sweden and did his PhD there, and then went to MIT, where he was there for 3 years? 3 years? 3 years. We did a lot of work while you were there. And then came to Culham and was the stalwart of the Culham theory program until shortly before I arrived at Culham. He was made a director of the Max Planck Institute in Greifswald, where they have just completed, and I think he'll be telling you about one of the most interesting new experiments in fusion, the Wendelstein experiment. Per is one of the great speakers in our field, so I'm looking forward to this talk very much.
Thank you, Steve. I'll start with two remarks. First, this is a talk about plasma physics and fusion, of course, but knowing that most of you are not plasma physicists, I've stripped out all the plasma physics from it. I'll try to speak for about an hour. That's fine. I can take questions during the talk as well as afterwards. The story starts 65 years ago with a headline on the front page of the New York Times. The Argentinian charismatic dictator Juan Perón had a press conference the day before announcing that scientists in Argentina had realized controlled nuclear fusion, which would bring energy and lasting glory to his country. So on. This is the actual headline. It used a thermonuclear reaction that does not use uranium. They had already built a fusion pilot plant. The reaction required enormously high temperatures of millions of degrees, was said, and these claims were met by skepticism, by healthy skepticism from all the leading physicists of the world, such as Enrico Fermi. But a few people started thinking seriously about fusion. Some people already had. And one of them was Raymond Spitzer, who at the age of 36 was head of astrophysics in Princeton, already famous for his pioneering studies of the interstellar medium. He was given this New York Times article by his father. He was just going off on a skiing holiday in Aspen, Colorado. And he started thinking about how you could perhaps make fusion happen. He realized that the easiest reaction to use is that between deuterium and tritium, which produces a helium nucleus and a neutron. Tritium is radioactive, of course, has a half-life of 12 years, so it doesn't exist on Earth, but you can make tritium from the neutron by making it react with lithium. I realized this was a suitable reaction. I will not spend any time explaining why fusion might be a good idea. To such an intelligent audience, I don't feel I need to make the case for fusion. But in Germany, that is sometimes different because it's nuclear.
Is that because there's not an intelligent audience?
This reaction, because the positively charged nuclei repel, they need to have high enough energy to get close enough to each other to fuse, so you need a high temperature. Of course, that means in practice about 100 million degrees. So that's 1,000 times the ionization temperature. So any gas will then, of course, be ionized. It will be a plasma. And it's important to realize that the ordinary collisions by the Coulomb interaction are much frequent than the fusion reactions. So this implies that the plasma will be in local thermodynamic equilibrium. You can't make fusion by colliding beams on each other, for instance, because they will slow down and lose their energy. The particles will lose their energy by ordinary collisions much faster than they fuse. But how could you confine a gas that is 100 million degrees? Well, Spitzer realized, as he was sitting in the ski lift, it is said, ski lifts were very slow in those times, so he had lots of time to think, that if you use a magnetic field, then the electrons and ions, they spiral in tight spirals along the field, and they can therefore only move along the field. So this provides confinement in 2 of the 3 spatial directions. And maybe if you bent the field into a circle, into a ring, into a torus, you would get confinement in the 3rd direction. But that doesn't quite work, as he also realized, because a circular magnetic field isn't homogeneous. It's stronger on the inside than on the outside. And in an inhomogeneous field, the particles do not do just that. If the field is slightly inhomogeneous, so if B, magnetic field, varies slowly on the length scale of the gyro radius rho, so that rho of the macroscopic length r is a small number, then the particles drift slowly across the field. So if we write the position vector as the center of gyration plus the gyration vector, then the center of gyration vector does move with a parallel velocity along the field, so B here is a tangent vector along the field, but it also drifts relatively slowly across it in the direction of B cross gravity, so perpendicular to the field lines and the gradient of the field strength. So this means that in a circular field, the particles will drift out like this, and the confinement time will be too short. You can derive these equations most easily from just taking a gyro average on the fast scale of the Lagrangian, realizing that each little gyrating particle then looks like a little magnetic dipole with the dipole on McNeil, which is an adiabatic line. So that doesn't work. There are 2 ways of solving this problem of the outdrifting particles. One solution occurred to Spitzer too. He had a very productive holiday. And this was the solution that also occurred to several others at the same time. It's called the Tokamak. This idea is usually credited to Zaha, but it was also thought of independently by others. In a Tokamak, you pass a current, here represented by red arrows, through the plasma. That produces an additional field in the poloidal direction, in addition to the toroidal field, that's the long way around the torus. So the field lines twist, like the black arrows. So the black field lines are that of the total field. Even if there is a vertical drift, a particle following these field lines will drift. Half the time it will drift inwards and half the time it will drift outwards, as I will show in this little movie here. So this is a particle following the field line on a magnetic surface. The field strength is color-coded. It's following the field line, sometimes drifting inwards, sometimes drifting outwards, but on the whole, it stays on the surface wave side. That's called the Tokamak. Spitzer dismissed this idea because he could see no way of driving the current in a steady state with the plasma. You need to drive a current of several mega amperes. This was Spitzer's unique insight. If you bend the magnetic field into figure 8, then Spitzer figured if the drift is into the board in one half, it will be out of the board in the other. It would cancel. Beautiful idea, which was unique to Spitzer. No one else at this time had this idea. And what is more remarkable than that there is no net drift is that the magnetic field lines then do actually not close on themselves. I will go into this a bit deeper now. Spitzer wrote a report dated July 23, 1952, and proposed Stellarator. He called this device the Stellarator, which was highly confidential, of course, sent to important people at the Atomic Energy Commission, to Los Alamos, to Fermi's Institute in Chicago. This is the original drawing of the figure 8 in his report. So what he envisaged was a 50-meter long tube bent into a figure of 8, 1 meter of diameter, magnetic field of 2 Tesla. This would produce 100 megawatts of fusion power, and it would breed tritium from lithium by the reaction I showed you. Most of the ideas here have stood the test of time. It's remarkably accurate. There are lots of details which haven't changed really. But it's both too optimistic and too pessimistic. It's too optimistic in the way that he didn't think of turbulence. In practice, there are turbulent losses. The confinement is not as good as Spitzer thought. But his report is also too pessimistic, because this was before superconductors, essentially. There were no superconducting coils at the time, so he was proposing to create this magnetic field by copper coils. That would lead to hopelessly large ohmic losses. You can just about make it with the parameters that he suggests, but he didn't know about instability either, so it would be hopeless unless you had superconducting coils. This is the first device that was built. It was perhaps not a pretty sight. Somebody described it as something that it looked like a kid had built it. But it was successful in the sense that it did achieve 500,000 degrees, though not for very long. The plasmas were quite short-lived. That was the first Stellarator. It was soon realized that you don't have to bend the magnetic field into a figure 8. Pretty soon the following idea emerged. It's called the classical Stellarator. So here there's a toroidal magnetic field created by these field coils, by these circular, toroidally, symmetrically arranged field coils. Then there are pairs of helical coils carrying current in alternate directions like this. That twists the magnetic field, so the field lines look like this, and they trace out the magnetic surface that confines the plasma. Remember, the particles move freely along the field lines, they drift across the field lines, but in this way they drift as much into the surface as out of the surface. I'll show a video of this. This is particle orbit in such a field. So what you see is the magnetic surface, the magnetic field strength is color-coded, and the particle happily does exactly what Spitzer suggested it will do. Right? Let's think about this idea of twisting the field lines. It's a highly non-trivial thing, actually. Let us unwrap the surface like this. So this is the toroidal angle. That's a short way around the toroid. This is a toroidal angle, and let's follow a field line. So it's periodic in both directions. The field line wanders around the surface like this. But on the average, it twists to the polar direction as you follow it around. So you can drive the winding number. It's called the rotational transform. Let's call it the winding number. So it's simply how theta, the toroidal angle, increases in proportion to the toroidal angle, asymptotically, as you go many times around the torus. There is something strange going on here. If we look at the classical Stellarator again, and let's apply Ampere's law to it. If I integrate B dr along a poloidal contour like this, if I'm not passing any current through the plasma, I will get 0, suggesting that there is no average poloidal magnetic field. For this reason, people found this idea highly counterintuitive. And people actually didn't believe that it would work I have been told by Princeton colleagues, until James Van Allen, who was a student of Spitzer, built a device that confined an electron beam. So how can we twist a magnetic field without a plasma current? Which clearly tells us that there is no net toroidal electric field. Well, it turns out that these are two different averages. What is the average toroidal field? Well, let us again unwrap our surface, and let us introduce coordinates psi, theta, phi, so that theta and phi are again the toroidal and toroidal angles. And let's now choose these angles in such a way that the field lines are straight, so they're not the geometric angles. Psi just labels the magnetic surface. It's like the distance from the center of the plasma. Let us denote the volume between two neighboring magnetic surfaces by angular brackets. Then it turns out that B dot grad theta over B dot grad phi is this winding number, iota. The current in the plasma is a different average. It's this average. It's V dot grad phi cos grad psi over V dot grad psi cos grad theta. So one is effectively the average of the covariant components of the field, and the other is the average of the contravariant components of the field. And they are not the same for normal orthogonal arbitrary coordinate systems, of course. So this is the one that is proportional to the toroidal current in the plasma divided by the toroidal current in all the coils. They're two different averages. Let's do another thing. Let us consider a tokamak again, where we have this magnetic field winding around the torus. Let us pick a point on such a field line and walk perpendicular to all the field lines until we come back to the field line that we started on, and then go back along that field line to the starting point. Then, if we integrate BDR over this contour, then clearly we're going to get mu naught times the enclosed current. But the first part of the curve makes no contribution to this integral because there B is perpendicular to dr. So this means that the entire contributions comes from this bit, which is then proportional to the enclosed current. So this means then that in a currentless device, as in a stellarator, where there's no plasma current, the perpendiculars to the field lines close upon themselves. So this is another way of purely geometrically expressing the fact that you can have a rotation transform, a field line twist. So in a stellarator, the field lines wrap around the torus, but they twist around the torus, but the perpendiculars do not. They close upon themselves. And it is perhaps surprising that such a thing should be possible. But it is. You can draw field lines like this and perpendiculars that do not spiral around the torus. One can indeed prove a theorem. Mercier did so in 1964. Well, you can prove that there are exactly 3 ways of twisting a magnetic field. This is a pretty fundamental thing. It comes just from Maxwell's equations. So if we consider the magnetic surface close to the center, so it's elliptical in cross-section, at least must necessarily be close to the center. And we ask, what is the winding number, iota, the rotation transform of the field lines on such a surface? You can write it as an integral. You can derive this integral. It's surprisingly hard to do so. It's about 10 pages of algebra. You find that there are 3 terms. So it's an integral dl along this what we call the magnetic axis, center of the device. The first term is the toroidal current density. So J is the control. So that's what's used in Tokamak. The second term, tau, that's the torsion. The torsion is it's a concept from differential geometry, which tells you how much a curve deviates from being lying in a plane. So if B hat here is the tangent vector along the field, and kappa is the curvature vector, then B cross kappa will be perpendicular to both B and kappa, and perpendicular to the instantaneous plane in which the field now lies. If you then ask how does this vary along the field, you get this so-called torsion. The third term has to do with the ellipticity of the device. So the ellipticity here is, if I define A as the logarithm of the major to minor semi-axis of the ellipse, and D as the tilting angle of that ellipse, then the third term has to do with the rate d prime at which this ellipse tilts as you go along the field. So if the cross-section is elliptical and if it's tilting as you move around the torus, sort of drags the field lines with them. This torsion term has appeared in physics many times. It's mathematically similar to the famous Berry phase in quantum mechanics. There are many physical examples of such a thing. One is if you pass polarized light down an optical fiber that you coil, the polarization at the end will not be parallel to the polarization in the beginning, even if the tangent vectors are. It will be proportional to the solid angle traced out by this tangent vector. It's again an integral of the torsion of the field. I went to the hardware store and bought something to illustrate this with. So this is a metal tube where I have drawn a field line, it's gone a little bit faint here, in red here, and the field line closes upon itself. But if you do this, if you add some torsion to it, if you do this, it twists, so it's free to move here. You can feel with your muscles what you need to do to get a rotation and transform. You need to have systematic torsion in one direction. If you do this, it won't twist. If you do this, it will. And this is the sort of figure 8 stellarator. I'll pass it around. You will feel with your muscles what you need to do to twist the magnetic field. That's a hydrodynamical equivalent too. We regard the plasma as a fluid. So this is the usual Euler equation, implicit Navier-Stokes equation with the J cross B force, that's the magnetic force opposing the pressure. And if we look for an equilibrium, that J cross B will equal to grad P. The magnetic force will balance the pressure gradient. So the magnetic field lies in surfaces of constant pressure. So these magnetic surfaces are isobars. Ampere's law then, instead of J, write curl B over mu naught. We get this equation for the equilibrium. So it's curl B cross B is equal to the pressure. This is exactly similar to something to the equation from the streamlines in an incompressible fluid. This is the Euler equation for an incompressible fluid. So here the convective derivative of the velocity is equal to the pressure gradient. If you consider a stationary flow, you have just this convective term balancing the pressure term, and you can write this equation like this. So curl of U cross U is equal to the gradient of something. That's the same form as the magnetic equilibrium term in the plasma, the equation in the plasma. So this means that there is a perfect isomorphism between incompressible fluid flows and plasma equilibrium, where the velocity of the fluid corresponds to the magnetic field, and the vorticity of the fluid corresponds to the current density. So what I'm saying here is that if you have a pipe that is toroidal, say, you pass water down the pipe, and if that has an elliptical cross-section, it will drag the streamlines around it, will create a swirl, an average twist of the streamlines, although there is no vorticity. So streamlines may twist even in the absence of vorticity. Twisting and vorticity are actually different things. This is what seems counterintuitive. So knowing this now, people have built many Stellarators over the years. You can do it any way you want as long as you twist field lines. This is the largest device until a few months ago in the world. It's called a Large Helical Device. It's in the National Institute for Fuel Science in Japan. It uses a pair of helical coils carrying current in the same direction. There's no toroidal field coils. It instead has these big planar colloidal field coils. This is what the magnetic surface looks like. This was the largest Stellarator in Europe. Now it's the second largest one. Here the magnetic field is created by these green circular coils which are displaced around the torus in this way, and a pair of toroidal coils which are blue and red and tied around upon each other, and it produces this rather fanciful magnetic surface. Looks like something Salvador Dali came up with. It's in Spain, of course. All these Stellarators suffer from a basic problem. Not all particle orbits do what I showed you earlier. There are orbits that get trapped in regions of strong magnetic field. This is familiar from the Earth's radiation belts. Sometimes some particles cannot penetrate into regions of strong magnetic field, and they will not circulate around the torus in the way that we saw. In a tokamak, they will be well confined, but in a Stellarator, they will do this. Let's look at the movie again, now to the end. The particles that do not get reflected by the magnetic field, they are happily confined. But in the local magnetic field wells on the surface, there are particles that bounce back and forth. They are reflected by regions of strong magnetic field, and they quickly drift out of the device. And this spoils confinement in Stellarators. Therefore, Stellarators never showed as good confinement as tokamaks, and were out of fashion for decades. We're trying to solve this problem, as I will now describe in the second half of my talk, in the Wellenstein 7x experiment. So this is a new fusion experiment in Greifswald, in the north of Germany. This is where it is. Few people know where it is. Even Germans have normally never heard of it. It's a nice place. It's close to Sweden, for instance. That's a lovely institute building. It's on the sea. I do recommend you to visit, perhaps in particular if you are interested in plasma physics. In Wellenstein 7x, so this experiment became possible only with the advent of supercomputers. So what was done was the following. One asked, is it possible to create, there's a great amount of freedom in shaping a toroidal magnetic field. There are many degrees of freedom, 40 or 50 or so if you estimate the roughly number of degrees of freedom. Can you use that freedom to improve confinement? So the magnetic field essentially is uniquely defined by the shape of the boundary. You write B as grad V, and that's good, and V satisfies Laplace's equation with Neumann boundary conditions. You have a classical Neumann problem that defines the magnetic field. So you can vary that shape of the boundary until you find a field that you're happy with, in some ways. Then you can, in a second step, find magnetic field coils that produce such a field by finding the current distribution on a surface exterior to this magnetic surface. You can always find such current distribution. And then you can discretize that and come up with magnetic field coils. So the idea is that you have a plasma here confined by a field with properties that you want. And they are produced by coils, which are hopefully buildable, although they do look a bit fanciful, especially if those to be built up as superconductors. But this is what has been done. So the field was optimized according to a set of criteria I wanted good nested magnetic surfaces, good equilibrium properties, good stability properties, above all small transport. So the number of orbits, the fraction of particle orbits that drift out has been minimized here. And you want coils that are reasonably simple, although you may not find these particularly simple. The industry didn't when they had to build them. But it worked in the end, as I will show. I will not go into the whole science of doing this optimization and what is meant by small transport. We'll just state that theoretically, at least in theory, it works. And just to show you a movie of what a typical particle orbit do in this field. So first here we have a circulating orbit, and it just does what it did in the earlier videos. But let's now look at the trapped orbits, the ones that normally the generic field just drift out. So here, it drifts around the surface that it started upon. On average, it doesn't leave it. This is what the great majority of orbits do, and thereby the calculated confinement in this field would be much better, an order of magnitude better, than in any previous experiment. And it should be good enough that it's comparable to the turbulent transport in tokamaks. So this is the theoretician's picture, of course. The work of the theoretician ends with the last magnetic surface. Then the engineers have to build something. I will try to give you some idea of the complexity of that undertaking. So here we have the last magnetic surface. The plasma is all confined inside here. It's 12 meters across. It's a pretty big device. And that we found from optimization. Then you need targets. You need heat flux targets. So somewhere, all the heating that you're putting into your plasma, in order that it get to 100 million degrees, comes out somewhere on the wall. You need to protect the wall somewhere. So the feed lines have been tailored to come out in certain places where there are actively cooled targets capable of taking 10 megawatts per square meter. That's 20%. The total energy flux on the surface of the sun is 50 megawatts per square meters. So this is 20% of that. But it is doable. You just have to pump a lot of water through these. So this is CFC onto zirconium copper targets. You need to have the bulk of the material copper that has high thermal conductivity, but you can't attach you can't attach graphite to copper, but you can attach it to zirconium, and that you can weld onto copper. Then you need a vacuum vessel, of course. The plasma is very tenuous. This vacuum vessel, well, it's a very complicated thing. It's a complete new thing in welding technology. There are 5,000 welding seams here. It needs to have a very good vacuum. Then you need the magnetic field coils that I showed you. So there are 70 of them of 7 different types, both non-planar and planar coils in blue and silver here. So they are the most expensive bit of the device. They cost 80 million euros when they were bought. Here you see those coils being threaded onto the plasma vacuum vessel. The coils are subject to great forces, 100 tons or so. So they need to be bolted onto a central support structure that looks like this, steel. They're not allowed to move more than a few millimeters, and everything needs to be mounted to that position, manufactured and mounted. Then you need a cryostat, a second vacuum vessel, to protect the coils. They are superconductors. They are 4 kelvin. The plasma is at 50 million Kelvin or 100 million Kelvin, so you have a great temperature gradient over 30 centimeters or so, from 4 Kelvin to 500, 50 million. So this is what the vacuum vessel looks like. You need many, many ports. You need that both for diagnostics and for all the cooling pipes. So there are 254 ports in this Swiss cheese-like looking structure. Very wobbly thing. Special equipment had to be developed just for handling it. Then you need the ports that go through here, a couple of meters long. They need to go through both vacuum vessels. You need very good thermal insulation. And this is what the device looked like a few years ago, 5 years into the assembly phase. So you see here the inner vacuum vessel, the outer coils, the myriad of cooling pipes. So the helium cooling pipes for the coils and water cooling pipes for the vessel. And you see the outer vacuum vessel, and well, lots of things I can't go into. And this is when the cryostat has come on. It's slowly looking more and more like a spaceship. This is what inside the vessel. We have pretty demanding working conditions. Up to 20 people have worked inside here at the same time. And it's difficult because once you're not allowed to step on any of these these pipes, right? Everything has to be vacuum tight. So every welding seam was X-rayed and checked several times. This is the device last year. Now there's so much scaffolding that you can't see very much. So in summary then, this is what the device looks like. It has a plasma volume of 30 cubic meters. It's 12 meters across. Magnetic field of 3 Tesla. So the total magnetic volume is just under a gigajoule. That magnetic field is created by 70 superconducting coils. So the electricity bill and the cooling plant limits us to 30-minute plasmas. But that's steady state as far as the plasma and the wall are concerned. The plasma is heated by 3 different heating systems, 2 kinds of waves, electron cyclotron and ion cyclotron resonance waves that resonate with the cyclotron motion of the electrons and ions respectively. Now there's neutral beam injection. That's when you use a little particle accelerator to throw in neutralized fast ions into the magnetic field. The electron cyclotron resonance heating is the main heating system. It's a very impressive system. It's 10 megawatts, 140 gigahertz waves. So these are 2 to 3 millimeter waves. 2 millimeter waves. It's the world's largest such system. These waves are created by gyrotrons. In the gyrotron, you accelerate electrons into a strong magnetic field, which is axial here, and their cyclotron radiation creates a standing wave, which you let out through a waveguide here. Then the transmission is optical. That's not by waveguides. So it goes through air like this. The waves are combined. There are water-cooled great copper mirrors like this. And this delivers then 10 megawatts of millimeter radiation to the plasma in a very nice way, without waveguides. We have expensive taste. There are the windows between to the vacuum system. They need to have very high thermal conductivity, and the best material is diamond. Why they have expensive taste? So there are diamond windows on these gyrotons, industrial diamonds. So the device was completed a year and a half ago or so, and was first commissioned for a year. Maybe I should show the video of the assembly of the device first. Let me interrupt my presentation and show you. So this is 10 years of assembly work. So here you have the first half module with the superconducting coils being threaded on the vessel, one after the other. One after the other. See the coils coming on the planar coils and non-planar coils. Now the first half module is ready and it's lifted into place. Then we work on the second half module. Goes on and is added to that module, and then all the supply piping comes on, the helium pipes and the current leads. And now the first module is ready and is being carried into the experimental hall, where it's put into the lower half of the cryostat. Then the lid of the cryostat comes and it's moved into position. And then one module after the other. There are 5 modules. In total, this is from above now. You see the modules being lifted into place, one after the other. Lots of pipes and ports are being mounted. Everything is welded together. Here comes the final module, the final the cryostat, and then all of the exterior things are added. Yeah, and that's the idea. So that was 10 years of assembly work in 1 minute. So. The device was ready to go, and last year, after a year of commissioning, we could look at the magnetic field. So the magnetic field has been carefully tailored. The assembly has supposedly been done to millimeter precision, but we want to measure that that's actually so. We have, of course, measured where all the coils are mounted, but you can actually see the magnetic field in a very nice way in Stellarator. So if you just evacuate the vessel a little bit and insert a cathode to emit an electron beam along the field, that electron beam will interact with the background gas or with the fluorescent rod that you put into the device. And you can sweep the electron emitter and the fluorescent rod and get beautiful pictures of your magnetic field. So this is what the field lines look like on the camera. You can actually see the field. Very nice way. So this is just, so the electron beam propagates about a mile around the torus, about 20 turns around the torus. The emission is from nitrogen and water, so it's air, it's moist air, right? And in this way you can measure some field components up to an accuracy of 10 to the minus 5. I believe this is the first time a magnetic field topology has ever been measured that accurately. 10 to the minus 5. On the 9th of December, we had our first plasma. So we had invited the press. We had 11 camera teams in the control room. 20 millisecond lifetime was that plasma. The temperature was up to 100 eV. So it's 1,000,000 degrees. That's enough for the press. It doesn't impress the plasma physicists. But so in the beginning of a device, the walls are loaded by impurities. You have to make plasma after plasma to wash them out, so to say. These were helium plasmas. We invited a physical chemist from Berlin to come and start the first hydrogen plasma a few weeks ago. And these are the best, this is the best performance to date. So we launched up to 5 megawatts of ECRH. Plasma lifetime up to 4 seconds now, as of last Thursday. Density is up to 10 to the 20. The normal density is solid. So this means something to the plasma physicists in the audience. Electron temperatures up to 100 million degrees. And ion temperatures up to 2 million degrees. The coupling between the electrons and ions is pretty weak, so and this is what the profiles look like. So to summarize then, Spitzer's Stellarator concept will be a pretty definitive test in Wendelstein 7x. If this doesn't work, I doubt that anyone will spend a similar amount of money on another Stellarator. The device has been completed, commissioned and taken into operation a couple of months ago. It should verify the theoretical predictions are correct, that fusion-grade plasma confinement can be provided by a Stellarator in steady state. It will be very interesting to compare the confinement, the turbulence, and general performance of that with Tokamaks. That's my summary. I will just end with an afterthought. This is the Ockham lecture. William of Ockham, he was, we know that he preached economy. It's futile to do with more things than that which can be done with fewer, for instance, he said. And I quietly wonder what he would say about Wendelstein 7x, which after all has 70 superconducting points of 7 different types, a different heating system, 5,000 welding seams, 254 ports of 120 different types, several hundred kilometers of cables, and a diverter, that's the heat flux target consisting of several 100,000 parts. Thank you.